Okay, yeah, so welcome to the talk I'm going to give. It's about OSCAR beyond groups well, about what I wanted to talk. Well, I've decided essentially to show examples of what one can do. Get some feeling of what's possible and how to do the things. Essentially, we yesterday seen some overview of which areas of mathematics are covered by OSCAR. So I want to focus on some particular for examples. Okay, and so my idea was to look into variant theory, give some example, then symmetries of number fields. So first, all this is of course influenced by groups. In variant theory, we start with a group and go to some polynomial ring with it. Here we start with the number field, and we are interested in some groups. Then one important point. Independent of the mathematical area, serialization of data provided by OSCAR, also interesting for users of GAP, as well as other systems. So that's something I wanted to show. Then I wanted to give one more flavor of example, how one can get speed up via Julia, and also having in mind that, well, for users of GAP, how they can benefit from that if they don't really want to use OSCAR, but just have a very efficient function. So again, it's just an example. And then, well, some example from reality how one can manage to use OSCAR functionality. Yep, for needs it's at time permits one more example. Okay, let's start with invariant theory. The setting is we have a matrix group over some fields. And so these are the matrices, and then we take a polynomial ring to be determinates. Well, we have seen already yesterday the group matrix group is act on the polynomial ring by some linear action prescribed by the matrix. So you multiply the vector of the determinant by the matrix, where one has to careful. Well, here we have multiply with the vector from the left, column vector of the determinants. Well, if we don't believe, just write down the only way how to do group action. Okay, but well, if we believe that this is a group action, then well, we can ask for, well, what are the fixed points under this action in the polynomial? And then one of the theoretical results is, well, if you start with a finite matrix group, then this rings of invariance is finitely generated, and then the natural question is, well, compute such a finite generated system. So that's one of the tasks what people are interested in. And well, in order to solve this problem algorithmically, so not an example, but just well, give an algorithm, a function which takes this input and then spits out the generating set. Well, this requires algorithmic basis and group theory. So we are in such an area where these two areas are used together. And well, if you have just support for one of them, you can't really do this. So in OSCAR, well, we have these available, so it should be possible to do it. Yeah. A very small example. So we take two matrices or integers, rational fields. Here. We compute where the matrix group generated by them. Well, they are commuting, so this is a line for a very small group. And we ask OSCAR to compute the variant ring. And then a function which gives us a generating system is fundamental variance. So call it, in this case, we get these 5 polynomials which generate the invariant ring, and that's the result. So one important variant of the invariant ring, so I have to think of the invariant ring is the volume series, which well, if we write it as a series, well, it encodes the dimensions of spaces of invariance for each dimension. So the group action, it preserves degrees of polynomials. So in fact, as a vector space, the polynomial ring is a graded polynomial ring with this group action acts on subspaces of fixed dimension, and so the dimension of variance in each dimension is given by the series. So we see that in this case, Monian series starts with 1. That's not surprising. The constant terms are always invariant, so we have a one-dimensional space of invariance of 0. Then we have one dimension for V1. This is generated by this polynomial, which we got. Some of these invariants. Then we have a 4-dimensional for degree 2. This polynomial is degree 2. This polynomial is also. This is 3-dimensional. And then, of course, the square of that polynomial. What's the counts of an invariant? And so on. Looks like this. Computing the Monian series, in fact, is possible just by using the group. So there are algorithms which need not compute with polynomials at all. We can just give it the matrix group and then compute with the Monian series. But getting these this generator themselves, this requires really working with the polynomial. That's really a much stronger information. Okay. So symmetries, number fields. There the question is what exactly one wants to do. So one starts with some number fields, which one can create by first write down a polynomial, and for writing down the polynomial, we start with a polynomial ring, or Q, and like that takes a polynomial square minus 7, got a polynomial, and then K is this number field generated by drawing the root of this polynomial. And then the most explicit things one can do about symmetries of a number field is work with the field automorphisms. That can be done. So we function of morphism group, and can even ask for given this permutation, this automorphism group as permutation group. And we get back with G. And see the first generator of the group 1, 2. Cannot be larger because it's 2, so this is just a cyclic group of 1 or 2. What else did we expect? And this second return value here from the automorphism group, it's a map which gives us access to identifying this permutation group with the actual automorphism of the field. So if we apply it to this permutation, gives us this field automorphism, and we can apply it to a generator of this field, and it's meticulously signed. So that's the most explicit way how one can deal with it. But this works in small cases. Yeah, so something which requires lots of computation to explicit field automorphisms. If the degrees of these fields get bigger, it will become very, very expensive. So what else can we do in order to deal with field automorphisms is talk about Galois groups. So we have seen already yesterday that there is, say, gap, this functionality, input polynomial, give me a description of the Galois group as an abstract group. Then the return value was just some identifier. This is the nth group of in the transitive groups library of a given degree. And this is then abstractly the Galois group, but it's not connected at all to the fields which one has in mind. One talked about this polynomial. And the approach taken here for Galois groups, this is somewhere in the middle. So we have a group which is connected to the field in the sense that it knows how it commutes the roots of the polynomial, which I will feel, but we don't have access to these explicit field automorphisms. So this is a little bit weaker information, but it's also cheaper to get. It works also for larger degrees of the polynomial. So that's somehow how does it work? Let's take here the polynomial x to the 4 minus 2. And what we get here is an automorphism group of order 2. Why? Well, if we take a root of this polynomial, say the fourth root of 2, then of course this field generated by this root is not a splitting field. We don't get all 4 roots of the fields, so we cannot commute 4 roots plus 2, and so we get a smaller. This field extension is not a splitting field. And well, dealing with Galois groups means, as convention says, that we are dealing with a automorphism group of the splitting field. But here the idea is we don't want to form the splitting field explicitly, but well, try to avoid this, and still we want to be able to work with this Galois group. So in this way, we avoid very large field extensions, still get a lot of information. So what we get here, we ask for a Galois group of this field, is really a commutation group of order 8. Well, what I said, we get still some information about the action of the roots. This is given by the auxiliary object here to see some Galois context, which stores a lot of information about what we have computed. For example, we can ask it for, well, some approximations of the roots which are sufficient for recovering the action of the group on these roots. In this case, something which is done over some elastic fields. So we get this information here, and well, here with precision of these values to 2, it's sufficient, and it's also not using too much space here on the side. So we see that well, we can work with these Galois groups and do polymorphisms of field extension in a very explicit way. And behind these computations, well, is a lot of code for number fields, which is necessary for able to compute it. Okay. The next point, serialization. There was a more technical point. The idea is, well, we are computing data in OSCAR. And sooner or later, we want to store them somewhere. So it's not just starting a session, doing a computation, having a result, and then leaving the system and it's done. But well, we want to continue the next day. We want to send the results to some collaborators, and then they should be able to continue with these computations as well, without starting everything from scratch. So you don't just send the input and say that, well, after 3 weeks, I got some nice results. Well, here you can repeat it. And then after 3 weeks, the collaborator can also continue with something. So being able to store these data, read them into a session, and then continue there, that's something which is important, useful. And also say, if you are publishing some paper and it involves computations, and usually you will have to refer to some data, and well, people who read it, or referee, at least who is reading the paper, will ask for this data in order to confirm what you are claiming. So it's important to be able to have the possibility to store these data in a format that is readable into the session, and can be used to repeat these results and confirm these results, or perhaps continue this and compute more from that. Okay, so the idea is we have some OSCAR data, we want to save them to a text file. and loading this file into another OSCAR session, same OSCAR session usually doesn't see them, but another new OSCAR session. And this should produce objects with the same meaning and also the same internal structure. So there are dependencies between these objects. You have several groups and their elements. Well, after reading all these things back into the session, they should have the same relation to each other. It may be different objects, so perhaps some information which you have computed is not available in these data, so something may be recomputed if you ask, say, for the size of a group or so, but essentially you have the same objects and can do the same things as the original session. Okay, and then exchange these data with collaborators, but also if necessary or if possible with other computer algebra systems. So maybe that this file format can be understood by some other system. I think of Sage or Magma or whatever. If these systems have the possibility to interpret these data, then it's possible to exchange data between different systems. And therefore, this format should be not too complicated, but still rich enough for being able to reconstruct these objects. Okay, this format should be very standardized in order to give other systems also the ability to have an interface to this format, and then it's possible to exchange these data without too much hand editing and retyping and whatever. Yeah, okay, that's the theory, that's the aim, what one would like to have. And one formal way how this has been formulated in 2016, these data should be fair. There are these fair principles, where this means this is an acronym for the F stands for findable. So one should be able to find these data. It's not just some comment. On request, the author will send you the data which are necessary to verify the computation or so on. Should be available somewhere and maybe even public enough such that it's possible to find this automatically. Okay, it should be accessible. So rules should be clear how to access these data. So for OSCAR, it will be easy. It has been written by OSCAR. There are functions in OSCAR. Read the file and everything will work. For another system, it may be necessary, if there is not yet an established interface, that there are rules how to interpret, and then it may be possible to use this. The easier, the better. Accessible. Interoperable. Usually one does not use just this one file then, but maybe you have a computation in several systems and they all have to work together in order to prove your theorem or whatever, find your example and construct something. And so these data should interact nicely with others, which that's from somewhere. And then, as I said, it could be reusable, especially also in other systems. So data format should make this possible. And so there is lots of publications about how one should do this and how this is done in practice. So the key word for that is the RWTH project. So it stands for Mathematics Search Data Initiative. So, you are interested in that, and as soon as you have some data which are subject to these things, it makes sense to yourself about. For example, there is here this paper by some people which are also working on the OSCAR project. This is some documentation from last year, where they describe this. Done in OSCAR and produced also to have more general interest. Okay, rule of thumb. First of all, think about such questions before you create huge amounts of data, and then later you have the problem to convert them into something which fits. Really makes sense to do this, store them as easy as possible. And yeah, one rule of thumb is better don't rely on some particular language. So, for example, if you have some gap data, then it's not a very good idea to store in your files explicit gap code, which is then run by reading the file, uses a lot of functions and very difficult code, because well, other systems will more or less be unable to interpret what is in these files. So, okay. Now, so what are we doing in OSCAR? So just getting an idea of how such data looks like. So we start with something very easy, vector of integers. Here we find this 1, 2, 3. We save it to a file, and the converse, the reverse direction is to load this. Then this results, it should be easy to the original vector. That's good. How does this file look like? So, well, for this small vector, it looks very complicated, but the objects get more complicated. This overhead, you see, will be smaller. So we have first some identifier of which OSCAR version has produced this file. So one may think of something which in later OSCAR versions is handled in a different way. So perhaps think of a group where some more attributes are stored in a newer version of the serialization. And then if you read the old version of the file, then this load function should not expect something which is not yet available in this older version. So that's unfortunate that this may happen, but in fact it's well, maybe an improvement to change the format to make it richer or even to correct. Okay, so the version of the system in there. Then, well, the rest is more or less well, easy to interpret if one has a guess what it means. So we have a vector which is stored there, which consists of integers, and well, it's even the exact Julia type of integers which is in. And then the data themselves, these are just well, these integers way which does not have the danger of overflow in some systems. So if you think of very large integers, if you will store them as integers, then some JSON parser may not accept these very long integers and then have a problem. So these data are more or less all stored as strings, which is safe. So this load function has to return these data, this information to the integers, which will be unique. So, okay, that's a very easy example. So a little bit more complicated if we have a vector over a finite field. So we take 3 elements, the 1, 0, field, vector, and again we save this to a file. Okay, our identifier of the version. And again, we have the description of what this, what type this object has. This is a vector of, well, in this case, some type of finite field elements, which, well, it's known to OSCAR. Other systems would have to interpret that. What does this mean for me? And then, well, data 1 and 0 of the field that fits. But yeah, this finite field element, this has some more complicated identifier here, some key, which is then later explained here in this additional refs component, which we did not need for the vector of integers, which says that, okay, here I have some object which has this key, and it's a finite field which is described by the data 3 in this case. I have the field of all the 3, and this 3 is enough to specify which field is meant. You can imagine that if we take a non-prime field, it's getting more complicated because we have to encode also the polynomial which defines this field. So, but we see how the idea is to explicitly describe a way to reconstruct the object. Okay. Yeah. Here we have example how we do this. So again, we note well, we take the vector, we say it, we load it, it's the same. It's not identical because well, the function load it created a new vector. So that's well, it's not really the same object. But what is identical is yeah, the finite field, which is over which these vectors are written. And this is because we were using the same Julia session, so this finite field still existed. And using this, this key, it was even possible to identify the field which was used and to assign this vector to exactly this field. I've seen yesterday that finite field elements, they all have a parent. For the parent, it's important that it's compared with respect to object identity. So here, these two vectors, that they live over the same field, and we can imagine that if we would do this in a new OSCAR session, then deserializing several such files would then manage to assign them to the right field, maybe say, generate this new fields for each of these vectors. Okay, and yeah, even more complicated. Well, let's try to serialize some elements of a free group. So we take the generators of the free group. We save them, we load them. Same effect. Well, this vector is new, but the free group below is identical. So this is maintained. And well, this is how the description in the file looks like. So again, we have a vector of something which consists of well, it is FP group elements, some elements of a finitely presented group. And we expect already that we need some identifier to describe what the group is in order to assign the elements to the right group. Data are the words in generators which describe these elements. So here we have the generators. So this is the first generator to power 1, and the second generator to power 1. This describes the generators. So that's enough. And then, well, the reference, here we have our key, which tells, this is a finitely presented group. And this finitely presented group needs another auxiliary object where it relies on. And this is the underlying get object. So we have here another group which has the type get obj, and where we get it is a free group with some more information. Again, well, this is the names which are used there, and this is a description how they look internally. So the idea is, in order to reconstruct this vector, we have to first we have to go to gap and create this free group. On the basis of this free group, OSCAR knows how to create its free group. And then one can create the elements of this free group and gets objects which have the same internal relationship as they had before. Well, that's the idea of serialization, and one can see that if this can get be nested arbitrarily deep if the objects get more complicated, but in principle, this is a recursive process which works. Okay, so this is in the format which OSCAR currently provides, and well, that's what we can offer. All right. Yeah, then one example of well, how to use Julia's compiler for making our code more efficient. So here we have an example: positive integers q and z, and then we have the condition. We know that z divides q to the n minus 1. We are interested in the q-adic expansion of this. Well, this is an integer q to the n minus 1 divided by z. That's well, this is not just a arbitrary example. Well, there's some paper where exactly these calculations are necessary. So there are, this paper defines some algebras which depend on q and z, and the basis of this algebra, it's we are just parameterized by these values, so multiples of this due to the -1 over z. Okay, so this is, we take for granted that this is interesting. Somebody wants to do these computations, and yeah, so how can I do this? Well, if we do it again, there is a function coefficients q-adic, which one can use, so why not? Our input is, well, z 9439 q22 and z -1. Then we e is our number which we want to, well, for which we want to compute the coefficients, and then we see that does this, and in fact, it's a very long coefficient list, so almost 10,000 coefficients long. So this is a very good number. And well, if we now measure how long it takes to compute these coefficients, then this is about well, 1.6 milliseconds for this value. Okay, that's not very good, especially if we want to do this not just once. So, well, what can we do better? So, well, in this case, we are cheating a little because in this special situation we can do it in a completely different way. So, well, I can show that these coefficients, well, the reversed vector of these coefficients, it can be computed by just well, computing remainders and quotients. In particular, well, we need not write down this big number e at all. So all we need is well, we have that q of n, and then we well, during this computation, all the numbers remain small. Okay, but again we try this. This is already well, faster. So here we need just less than millisecond, so 1/3 of a millisecond or so for such a computation. That's special, but still it's not good. Okay, now yeah, we have Julia as a competitor, which well, promises that by compilation I can do these things much faster. So we write a Julia function, which does the same. So taking this get function and translating it to Julia, but due to the fact that there is a different function, it's even a bit shorter. So we take this function and here the chair marks package was mentioned before for measuring the runtime. And here we see that well, this is now 34 microseconds for this computation, which is well, compared to the effort which we had to write the Julia function, quite okay. All right, but of course this is not the whole story. Yeah, what do we have here? We have a Julia function which already knows that these z, q, and n are small integers. Yeah? So throughout the computations, all the numbers remain small, and the compiler knows this and uses this. If we would have started with this naive approach from the beginning, write down this very big number and then compute the coefficients, this compiler would have problems because, well, first of all, it requires a big integer, and then the arithmetics in Julia would have to deal with big integers for the whole time. So, and that way we cannot expect such a speed up just because we know how to do it with very small integers. We can well, benefit from well, these abilities of Julia. So what I mean is we don't get this speed up for free. So you don't just take some code from one language, translate it literally, and then expect that it is fast. So Julia must have a chance to also use the information which is there and in order to get this speed up. Okay, so just one example. So well, the message is, yes, it is possible to do this. One has to work a little bit perhaps, and sometimes even one has to be lucky to be in a situation where this really fits. Yeah, but it's not for free, but it will. Okay, so much about that. And then now some example from this summer. Graham, he's not here now, but he had told that well, we wanted to do some computations with square roots of integers. And if these integers are not very, very small, then what GAP provides is really bad in terms of efficiency. So, well, the square roots provided by GAP, they are just well, elements of cyclotomic fields, and so you need just not just two coefficients for describing them, but well, essentially n/2 coefficients to do that. So they are not very good. There would be some GAP package OLG, which well also had this problem, and they have done an implementation of exactly such square roots, so fields generated by square roots of several integers together. So that's also quite nice. But well, in fact, it's still not easy to deal with that. So it's well, it's better but not good. So well, in June, well, the authors of the package, it was Wilhelm Graf and Friedrich, they asked for, well, why aren't we able to use this OSCAR's well, algebraic closure of the rational numbers in GAP? No? So as we have seen already, example where this algebraic closure was used. Well, the idea is to have the elements stored in two ways, in an algebraic way and in a numeric way. So we have an approximation of the value in order to do some, say, comparisons bigger than 0, smaller than 0, and so on. And in order to identify which root of the minimal polynomial of this algebraically described number is meant. So that's how it works in OSCAR. It's available there, and well, why can't we use it in GAP? So what is necessary for making this available in GAP? So yeah, one needs some GAP objects which know about OSCAR objects. So some wrappers for these OSCAR objects, as we have seen in this talk. We have to provide arithmetic operations for these new objects. So essentially dedicating to OSCAR. So the sum of two of these wrapped objects is just given by the GAP objects defined by the sum of these underlying OSCAR objects. So on. Difference, product, quality also. Then, well, you also need a function that does what they actually want. Then we take polynomial and do some root, and then later work with the square root of this polynomial with this root of the degree 2 polynomial. Then, well, they also need a complex conjugation, which is also available on the OSCAR side, or not problem. And then, well, also important, real elements in the field, we want to check whether they are positive or not. Also something which can be done on the OSCAR side. So essentially, just knows how to delegate the work to OSCAR. And at the end, in order to define formally some algebras over this new field, need a field object in GAP, which claims to know everything about these elements and give the information needed by GAP. Okay, and well, in order to do this, well, one needs about 200 lines of GAP code, which are very straightforward. So essentially, it's clear you define just these operations, addition, subtraction, multiplication, division, and so on, and just delegate. That is very generic. And afterwards, it works. So currently, this code is placed in some GAP package, which is part of OSCAR. So there is an OSCAR interface package. So this way, as soon as you have a GAP which runs on Julia and has OSCAR loaded, this package is available, and we can use this code. So, so in GAP we can then say, okay, give me this field, the algebraic closure of the rationals. Give me the identity element, give me the 0 element. 0 is smaller than the 1. Okay. We can compute square roots of elements from the field. Then here we see this is something which is borrowed from OSCAR. The way how OSCAR prints these elements is now also shown gap. So we can create a matrix over this field. We can ask for its determinants. We can ask for the minimal polynomial of the matrix. We can ask for the eigenvalues. And well, for this functionality here, determinant, creating matrices and so on, nothing had to be added to gap. So this is completely generic. So essentially, we had to provide the arithmetics for this field and a few functions which are implicitly needed. So this square root method, for example, this was necessary. This clear that this cannot be done if one does not know how the elements look inside. And then this is working. So in principle, that's already something which the Willem and Heiko can work with. So very easy. So just a very small thing to be added, and we have some OSCAR functionality exported together. Okay. And yeah, you have more time? Yes, I have. No? Okay. Then one more example. What one can do in beyond groups, but starting from groups. So suppose we have a group G, then have a matrix of integers, which are the rational irreducible characters of G. We need not know what this is, just if we have a group, we can compute that. Integer matrix n by n, and the first row of the matrix is just ones. The columns of the matrix are indexed by the conjugacy classes, G. And then we have a subset of the columns which are indexed by the elements of prime power order in the group. That's our setting. From now on, we need not care about the group. We just focus on this matrix. The question is, well, is there some vector m, which is not just one followed by 0, so which does not describe just the first row of the matrix, such that multiplying this vector with the matrix, so forming the linear combination of rows of A with these coordinates. This is something which is non-negative. Well, the first entry should be 1, and well, when the next important condition, the values of the linear combination should be non-zero for all positions in this subset of corresponding to the prime power order n. So this is the game which we have to come up with. So is there such a vector? And so the first idea which one has is, okay, let's look not just at the integral linear combinations, but at the real linear combinations of the rows of A. Then, well, non-negative points may form a simplex. And some geometrical interpretation. And well, for the simplex, what we ask for is, well, is there a lattice point for which star is somewhere here behind. So this condition is satisfied. So now we have reformulated our problem in terms of this geometric property. And well, in fact, once we are here, we can also a priori say that, okay, we are not looking for just non-negative vectors, but in all those columns which are interesting for us, where it should not be 0, we can also ask that the value should be at least 1. So this inequality, which also gives us simplex, which is a little bit smaller. And then the solution for that, well, they are exactly the vectors which we are looking for. So we need not afterwards check for this condition. And luckily, in OSCAR, via this Polymac system, we have functionality for creating some simplices and well, enumerating lattice points. So how does it look like? Now we take the group A8 here. So this is just a starting point. We load some package which adds a little bit of OSCAR code just that deals with this problem, or not very much. We take the character table of A8, and then the simplex which we asked for is given by a function from this package S characters. So P is now the simplex. And then we ask for the lattice point, again, OSCAR function there. And we get, first solution is, this first row of the matrix, so every position filled with 1. And then we get a second solution, which is, the proper vector which we have asked for. So this is an example which, in fact, answers some question which Jean-Pierre Serre asked in some paper whether such vectors exist. So here we have an example where this works. Okay. Now, once we know we can do this, perhaps we can do it easier. So if we're interested just in the existence of some solution, not enumerating all of them, we can also argue that, let's interpret this input data as a mixed integer linear program. We prescribe some target function. So say, some of these coefficients should be optimized, minimized, maximized. Then this will give us an optimal solution with respect to the function if there is solution. Okay. And here is some code which implements this idea. So what we take is this S character simplex, which we have seen where looking at the lattice points also answers our problem. And then, in order to set up this program, we have to know how long the dimension of the problem. So it's going to be this D. And then there's a function solve this problem with this target function for once. And then if this program found a zero vector as solution, then this is not interesting for us. So then it fails. But if it is non-zero, we have found a solution. And here in this case, we apply it to the problem before. We see that this program fits out the second vector which we have found. And in fact, this approach, it's weaker, of course. It's just one solution. We don't know whether there are others, but it's much faster than concluding all these solutions. And it works also for larger examples where this first approach fails just because of overflow. Yeah? So there are matrices which are then quite big, 40 by something matrices, and then either Juliac crashes because of exhausting the space, or runtime is so long that we even don't reach this point. So so in fact it fails because of these technical conditions. And with this approach, give me at least one solution, we can do this. So for example, here we have a big character table, so a big group. And if we ask for one solution, then that's quite quickly second vector and also finds one. Okay. Yeah. In fact, this was not the whole story again. So we are interested also in more general problem, and then there our matrix, it's not a matrix of integers, but it has entries in some number fields. Yeah? Again, we are combining group theory and number theory and this polyhedral geometry, and all this works nicely together in OSCAR. So if we deal with a matrix over a number field, then this exhaustive approach, this first one, it still works. Why? Because this matrix over number fields is compatible with the programs of Polymac. So computing the lattice points and computing whether some numbers are positive, some numbers, well, real numbers are positive or not. And so these programs can deal with that. They send these values. Therefore, it simply works. And so we need not change the program for that. That's perhaps those places where we had suddenly assumed that they were integers. Okay, so what we need is just we need that field arithmetic and positivity checks are carried out properly by these functions. And luckily, they do this. Okay. Yeah, of course, the drawback in this more general situation is that, we cannot do the trick to deal with a smaller simplex in order to satisfy a priori this condition on the negativity on these special positions. So what we have to do is really take this bigger simplex and check the conditions afterwards. So, which is again sometimes a problem because there are very many solutions and it may have an overflow. But because of this different situation, this mixed linear programming approach does not work in our case, because if it comes up with a solution, it may be just one of those where we should start satisfied. I cannot guarantee that this is a priority. Okay, so but that's this example, which again is some real world example. So that's all what I wanted to talk about. Questions? Nope.
How do you program solve?
How? That's, I'm not an expert for this. I'm just a customer. So
do you use built-in functions, or is it?
No, I think this is a function either from the polymath system or maybe even from some standalone which is incorporated by the polymath system. So there are even, I think usually there are several algorithms which they have to choose from, and then given the input they decide which to use. So, but I don't know.
So I think that you skip. So there is a lot of these optimization things. So there's also interface for Ruby and so on, of course. But in this case, I think polymath is used here.
Yeah, well, one can look at the code. Yes.
What are we use was the edition for break closure of the rationals.
And break closure of the rationals. So yesterday this was already mentioned briefly. So we have an element with the device. So it's a root of some polynomial which one can write down exactly. And so
so you are seeing that you have cooked an algorithm.
So the algorithm. So the representation of this element means each number knows it is a root of a certain minimal polynomial. Plus information which root of this minimal polynomial is by an approximation. So this forms the element. And if you form sums of such numbers, again, the result must be represented this way. So you have to come up with a polynomial for the sum, asking approximation what it is. And as soon as you are uncertain, because the approximation of the value does not distinguish the roots, you have to go back and compute with higher precision in order to make sure that you describe the exactly one number. So it sounds horrible, but it works.
Yes, but you have so it means it is a good achievement. How do you prove that it's correct? So you have a proof of that.
So I think mathematically you can describe numbers like this. So I think the point is just, is it in practice usable, or does it become so expensive that well, it's useless? So I don't understand what's the problem about correctness.
Oh, you need to have enough precision.
Yes.
To be able to
Yeah,
decide.
yes.
It's in that.
So you can ask, so this comes from Flint, in fact, so we can ask Johnson about this.
But you have also other different strategies for doing it. It's not,
Right.
but for instance, I mean, there is a paper of Alan Steele about implementing algebraic closures, fields that you can also present.
Yeah.
And so you didn't look at this work.
Well, again, I'm the customer. I took this functionality, which is available.
Okay.
So,
Okay.
yeah.
Okay, sorry. I missed that. So you just took the function which were in another library and
This part of OSCAR, in fact, yeah, and then ask where in OSCAR is the implementation, where does it come from, in which package is the source code really located. But yeah, the customer, this functionality is there, and one can use it for such application.
yes, but yeah, so how do you check that also the functionality that you use are correct?
Oh, how do you check that everything is good? I mean, of course, there can be bugs in the code, but the algorithms are, actually, these are not so hard to prove that they are correct. Of course, mistakes can happen, so I'm not going to claim they're nothing, of course. But I mean, you have bounds, how many digits, how many precision you need, and so on and so on.
I think you are, so there's some kind of guarantee about the classification that computation have.
Yeah, but you have approach. Okay, that says that you have approach with from the past 5 years, 10 years, which has the advantage that they give you also a formalized proof of the way that you do it, and you avoid some redundancy and some rotations. That's I was wondering if so I was using. So it is the naive way of doing it.
In a sense, it is naive. Yeah. So, well, again, in practice, it seems to work in some examples. So, well, usually the field extensions which occur are not getting that big. So, well, of course, larger these fields become, these more complicated and then expensive, complicated that.
But if you want to know details again, I mean, you should talk to Frederick Johnson because it comes from calcium art films. It's this code. You've also integrated it into OSCAR, and so he will be able better than us. We are seriously.
I was just curious.
Sure, of course. No.
And also, I mean, okay, I was curious. I can explain why. I mean, OSCAR is supposed to be unique to use software. So I was wondering if you were trying to find, for instance, let's say the best new algorithm or the best new approach to implement it.
Right, so
That's what was my question.
Well, so
just
that-
a purely naive question.
yeah, but perhaps I said this also yesterday in this talk. OSCAR is both new and old, so tries to put up a new system from well established old components which are there. But of course, many aspects these systems are old and therefore perhaps not state of the art in certain directions. So, but well, we are not aiming at inventing everything new and well, trying to replace everything by something better. We'll just the main idea is take what is already there, put it together such that we have these well synergy effects that we can do things which we could not do with the single components. And then if we see that something is not working well enough, we can, well, these places try to do something better. And so we have just finite resources and
Yeah, I understand. Then I miss.
Yeah.
So naive, so it's also a naive question is what is the difference between OSCAR and SAGE?
So one point which we usually try is we want a very close connection between the systems. So Sage essentially aims at making things available and by making the systems interact in some way. But here we are able to make this as close as possible because well we have access to people who are working for this subsystems. So we can improve something in GAP. We can ask people to improve something in Polymake. Let's say make these OSCAR field elements available for Polymake's functions. This was not something that was from the beginning available, but well, as soon as one sees that, okay, now we can write down some polyhedra where the coordinates are such field elements. It makes sense to think about using or allowing these field elements in the functions, and then these programs have been improved in order to make such computation possible. So that's one of the ideas which I think is well, it's striking, but having the possibility to improve these subsystems in some concrete points, this gives us immediately some.
So in particular, you have a way to represent the data internally, which is coherent between all the different systems.
Oh, well, that's perhaps too much.
Well, but no, but still detailed from the lines. So yes, so for example, one thing that we did during this project is that now those Polymake and Singular actually also use Flint. And so, for example, Singular used to use NTL only, and now it still can use it, but it must get with Flint. And Polymake now uses Flint, and Polymark presented Polytrope over some number field. And then Singular does the basis of this, and then GAP does something with the group and so on. They're all using the same Flint, and in fact, I mean, for the stars, they are using Flint in Sage, for example. Well, of course, now they benefit from this as well, so they're Singular will also use Flint. But before that, it was NTL, and then you have to convert back and forth and so on.
Yeah.
And communication, of course, is also quite different.
Okay, thanks.
Well, okay.